Hi everyone. So in this video, we want to talk about a topic that we kind of already covered implicitly, and we already learned a lot of this stuff in other contexts, pop for example. But what we want to talk again about is substeps, and specifically what we have in RBD in the main setup tab, the global substeps, the bullet substeps, and to an extent the constraint iterations. And let's actually start right away. The constraint iterations, as the name suggests, is important for the precision of the constraint calculation. Since we haven't talked about constraints yet, this is something we will look at later, but to be fair, I almost never change this, so this is kind of the least important of the three. What is more important is the difference between the global substeps and the bullet substeps, and we kind of already know that because it's similar to what we've learned in the pop chapter, because basically what we have is an outer substep setting and an inner substep setting. So the pop solver itself has substeps. That would be the bullet substeps. And then there is a global substep setting for the whole popnet, for the whole simulation world, so to say. Here, the substeps of the DOPnet. And it's the same for the RBD bullet solver. The bullet substeps are the internal calculation steps, and the global substeps are the whole simulation, and that is important, including the collisions. So when is this important? We have already seen a case where we need to change the substeps, and that is when we have to deal with jiggling small scale simulations. So for example, here our card house. And we've seen that if we run this normally, and I've already set the bullet word scale to 10 to solve the biggest problems. Also, I made sure that the collision padding is lowered. But what I haven't changed yet is the substeps. So when I run this, then I will see this jitter. Regardless of the overall result, what I care about is the jitter here. And we've seen that I would naturally change the global substeps because this is simply the safest bet here, because this changes everything about our RBD bullet solver. And this actually works. You can see it becomes more stable that way. What we could also have done is changing the bullet substeps though, because when we set this to also multiplied by 10, because both are technically multiplied, then we get 100 internal bullet substeps and we will get an equally stable result. So for this example, there's actually no real difference between the global substeps and the bullet substeps because we only have internal simulations, because we don't have anything that comes in as a collision object. We only have active objects. So practically, at least, there is no difference between calculating the bullet calculation 100 times or calculating the whole simulation 10 times, with each calculation creating 10 bullet substeps. So in this regard, it doesn't matter. If you're not sure, like with a DOPnet, just set the global substeps and you will be safe. Where this matters more is a case when we actually talk about external movement, so animated collision geo that we just saw in the video before. And I will mention this again, the best way of dealing with static objects that are animated is actually using the animated collision type. But in this case, I want to show you what will happen when we use a deforming collision, because then it actually matters. So what I have here is a very fast bullet projectile, the red sphere here, which is a collision object. So as you can see here, it goes into our collision input, and this is actually hand animated. And we will actually see a simulation later on that is very similar to this, because in the middle we have a mast, which is currently not in any way fractured or anything, but for now it's really just standing there. And when we run this, we can see that our projectile, because I set the collision type to deforming, is actually moving, but weirdly enough, it actually runs through. And when we look closely, this is not a mistake or anything where it moves past it or something, but it's actually really going through, as you can see. What is going on here, you might already guess it. Internally, there are actually currently, with the defaults, 10 internal bullet substeps, but since the global substeps are still set to 1, the external collision object is only read in once per frame. And that means if we have a case like that, which is totally not constructed only for this case, of course, where the projectile in its path simply never really touches our active object, then basically the RBD solver doesn't notice that there is a collision. Now, if you would try to change the bullet substeps to, let's say, 100 again, of course, you might guess it, it will not solve our problem because it will not change the amount of times our collision object will be read in. What will change our result is when we change the global substeps, even 3 will be enough, and then instantly, bam, you can see there's quite an impact because now the RBD solver recognizes, oh, there is a moment where a collision is happening. Now this, to be fair, is only necessary when you work with deforming animations, because this means that the RBD bullet solver has to read in our collision object every single frame and basically rebuilds it. This is why I showed you, without going through this again in the last video, that a better approach is actually to turn our deforming animation into an actual animation that RBD understands as an animation with the help of the deforming to animated node. And then we can switch back to a collision type of animated and still keep a global substep of 1, and our simulation will recognize our projectile just fine. So again, while deforming is possible and adjusting global substeps to solve the problems that come with it is a legitimate brute force attempt, keep in mind that I'm still recommending using the deforming to animated workflow. And finally, here's another example that is a tricky challenge for RBD. We have here a rotating box where I simply animated the rotation with an expression, and inside of my object I'm spawning new boxes, and it looks like this. And since I'm using currently the deforming approach under collision type deforming, and by the way, I use a concave shape so that we can actually use the inside of our box, of course. And with the default setups of global substeps of 1, this will end up in a lack of precision in the results. So you can see that some boxes will fall out of our bigger box. Easy to solve, because as we've seen, all we have to do is changing the global substeps to a higher number. 3 should be enough, and then the external animation will be read incorrectly and the problem is gone. Again, the problem of course now is that we have to calculate 3 times more than before. So again, the best solution here is actually to use our RBD deforming to animated workflow, which in this case will calculate, as you can see down here, a W, which is the rotation information on our packed version of our box. And then I can use the normal animated collision type. In this case, I still keep the concave, otherwise I would not be able to use the interior of my box as a collision environment. But I can keep my global substeps at 1, and this will be the most precise while also being the fastest approach. So there was nothing really new here, just more like a reminder or just a way of kind of bringing all the knowledge together that we've already seen. The bullet substeps is the internal calculation, mostly necessary when you have jittering. The global substeps are usually necessary when you use a deforming input animation, but you can avoid that by making sure you use the default and recommended animated animation workflow. So I hope this was helpful. Thanks very much and see you later. Cheers.